Introduction to ROS community. Since its birth, ROS has released over 20 official versions. Over the past decade plus, it has grown with an open source spirit, forming a strong community of OSRF, robot-related business, and developers. Developers are key to this ecosystem. Millions have contributed to code, driving ROS's prosperity. For an operating system, this ecosystem is crucial. For example, China's Harmony OS initially supported Android apps for ecosystem-related reasons. Historically, robot operating systems like Player died out due to a lack of ecosystem. ROS is loved by robot developers for good reason. Next, let's look at ROS from a developer perspective. Pure theory can be done, so I'll use examples and diagrams to explain. When something first started job hunting and attending interviews, the interviewer asked, "What do you think a robot is?" He replied, "A machine that can automatically perform certain tasks, like moving and cleaning, similar to a human." He answered this way because a robot's structure and behavior are quite similar to those of a human body. Let's take a simple action as an example. When you feel hot, you turn on the air conditioner. If we use a robot to simulate this behavior process as shown in figure 1-1, your skin is equivalent to a robot sensor, such as a temperature sensor that can measure temperature. Your muscles are like a robot actuators, such as a servomotor that can control angles. And the brain corresponds to a robot's decision-making system. The nerve connecting to skin, muscles, and brain are analogous to a neural network. It's easy to see that ROS's role in a robot is to send sensor data to the decision-making system and then relay the decision-making system's output to the actuators for execution. In 2006, Eric Bergen and Kenna Weirbeck found through research that robot companions at the time were spending 80% of their effort building communication mechanisms and basic tools for robots, leaving little time to refine the decision-making systems. More oddly, even within the same time organization, every time they developed a new robot, they would start from scratch to build the communication mechanisms and tools, wasting a lot of time refining the wheel. The time spent on refining the wheel versus new research by different companions is shown in figure 1-2. ROS emerged against this backdrop. Your smartphone may have already guessed that ROS is essentially a collection of software libraries with communication at its core and tools for quickly building robots. Also, ROS solved the problem of refining the wheel in robot development with the continuous advancement of robot software and hardware and the expansion of application scenarios. ROS has revealed issues such as the lack of stability, real-time performance, and security in communication. Hence, ROS2 has begun to take the stage. ROS2 uses third-party communication components instead of the ones in ROS1, making data transmission more stable and powerful. Additionally, ROS2 has introduced a new C++ standard, bringing significant improvement in code standardization and interface consistency. Therefore, in this book, we will introduce the latest ROS2. How does ROS2 go further than ROS1? With curiosity, let's look at the ROS2 system architecture together and uncover its mystery. So let's move on. Let's talk about ROS2 system architecture. To help you better understand ROS2, let's first take a look at its system architecture. The ROS2 system architecture can be divided into 5 layers: the operating system layer, the DDS implement layer, the DDS interface layer, the ROS2 client layer, and the application layer. First, operating system layer. ROS2 is built on Linux, Windows, and Mac OS system. This player provides ROS2 with various basic hardware drivers, such as network card drivers, common USB drivers, and common camera drivers. Second, DDS implement layer. As previously mentioned, the core communication of ROS2 is implemented using a third-party communication component, which is the Data Distribution Service. DDS is based on the real-time publish-subscribe protocol for data distribution, which is RPTS. Then, third, DDS interface layer. Since ROS2 needs to support DDS from different vendors while maintaining consistency, ROS2 defines the ROS middleware interface, which is RMW. Different DDS implementations provide a unified interface for the ROS2 client layer. For example, the DDS interface layer is like a standard of a USB interface, while the DDS implement layer is like the USB devices provided by different manufacturers according to this standard. Fourth, ROS2 client layer. The ROS2 client layer provides ROS2 client libraries, ROS2 client library which is RCL, in different programming languages. Using the interface provided by these libraries, you can call the core functions of ROS2, such as topics, services, parameters, and action communication mechanisms. Fifth, application layers. All programmers developed based on RCL belong the application layer. For example, the TurtleSim simulator and ROS-Qt tools that we will use later are all based on this layer. Of course, the robot applications that we will develop in the future also belong to this layer. After understanding the architecture of ROS2, I believe you will have a better understanding while combined with figure 1, 2, 3. Like this. Let's talk about the released versions of ROS2. Table 121 lists the current main ROS2 distributions and their end of life dates. By the time you see this table, there are already been new ROS2 versions released. For the latest data, you can visit this address. For the table, it can be seen that Humble Hawksville is the first ROS2 version with a 5-year long-term support, so this book will be based on this version for learning. Next, we'll talk about the features of ROS2 robot development. First, the 4 core communication mechanisms of ROS2 are topics, services, parameters, and actions. Let's move on. What is topics? Topic communication refers to a publish-subscribe communication pattern. Publishers send message to a specific topic, and subscribers receive the messages by subscribing that topic. The data flow is unidirectional. For example, we can publish a robotics position information to a topic with a specific name, and by subscribing that topic, we can obtain the robot's position information. Second, which is services. Compared to topic communication, service communication is bidirectional. Service communication consists of service server and a service client. The client sends request to the server, which is processes the request and returns the result. Next is actions. Action communication also involves an action client and an action server. Unlike service communication, the action server can provide feedback on the progress of processing the client's request and can be cancelled at any time. Action communication is often used for complex robot behaviors. Next, parameters. Parameter communication is mainly used for setting and reading robot parameters. So, what are the rich debugging tools in ROS2? In addition to the core communication mechanisms, ROS2 also provides a wide range of visualization and debugging tools. First, ROS is for 3D visualization. Second, RQD series tools, which is for visualization charts, images, and other data. Second, ROS2 back, which can be for recording and replaying data. Next, modeling and kinematics tools. ROS2 provides essential tools for robot development. First, TF tool for kinematics, coordinate transformation, and measurement. URDF file format for describing the structure, joints, sensors, and other information of the robot. Next, strong open resource community and application frameworks. In addition to the core tools provided by ROS2 itself, the open source community has developed a rich set of tools and framework based on ROS2. First, Gazebo, which is a powerful simulation tool. Next, Navigation 2, an application framework for mobile robot navigation. Next, Move It 2, an application framework for robotic arm moving planning. So, you know what? With such a rich set of tools provided by ROS2, you don't have to worry about not being able to develop a powerful robot. That's it for the theoretical introduction. I believe you are already eager to start your journey in robot development. So let's start it now.